We can continue the discussion afterwards. I should mention that we do have a visit by prospective graduate students here, so please try to leave a good impression. As we know, the future is with the younger people. So we just heard an excellent ITC colloquium by Genel that used to be an ITC fellow, and I hope the experience is still fresh in your memory and you have a positive memory of us. He's currently at the CCA, the Center for Computational Astrophysics in New York City. And will tell us some more about his work in a few minutes. We'll start with Jordan Eagle that will talk about chasing Pulsar wind nebula with Fermi-LAT, and then continue with Jonathan Fortney, who's at UC Santa Cruz. Here it is. And we'll speak later today. At lunch, he will discuss evidence for a dichotomy in the interior structure of Jupiter and Saturn from helium rain. That should be quite interesting to hear. And then Shai will tell us about CAMELS, Cosmology and Astrophysics with machine learning simulations. So not only we are doing simulations now, we are studying the simulations with computers as well. And finally, Nathan Sanders, that used to be a student here, and he's sitting over there, and is now in the private sector, will tell us about the second decade of international graduate student-led science communication efforts born at CFA. And I would like to remind everyone that Nathan initiated this, well, the Astrobytes, I guess, you were among the founders, which became a very big thing since. And also was involved in outreach in various ways and in organizing an annual conference, providing students that are interested in public outreach with the tools that they need. So we'll start with Jordan.
All right. Well, thank you for that introduction. I'm happy to be able to start the ITC Luncheon with my research project and be able to talk your ears off for, the next 10 minutes. So I'm going to pack it. Oh, hello? How about that? Is this good? Okay. All right. So yeah, I'm going to talk your ear off about the research project that I've been doing with Daniel Castro. I'm actually a new predoctoral fellow here, so I've been here for about 2 months. So what I'm really going to lay out is our motivation. Why are we interested in pulsar wind nebulae, and why do we want to image them with the Fermi-LAT, which is a gamma-ray space telescope. And so just as a brief refresher, pulsar wind nebulae are descendants from core collapse supernova explosions, of which also a rapidly rotating neutron star is also born. And so one of the ways that these neutron stars actually lose their rotational energy is through the generation of a pulsar wind. So that's what I'm really interested in. Pulsar winds are made up of electrons and positrons that are highly relativistic. They are crazily interacting with this massive magnetic field that the neutron star hosts, and so this causes them to radiate non-thermally from radio to gamma rays. We know a lot about pulsar wind nebulae for the most part, specifically in radio and in X-ray, but we are still hugely lacking gamma ray observations, and this is going to become important in terms of understanding how particles are injected into the pulsar wind nebulae, among other things. And so pulsar wind nebulae are complicated beasts. We really want to understand their evolution, and that is dependent on several external factors for the pulsar wind nebula, because it's one of many layers to a supernova remnant. And so the three biggest three most important layers of a composite supernova remnant is going to be the pulsar wind nebula that it powers, and then the supernova remnant itself, which is defined as the forward shock that's moving out into the interstellar medium. And so whatever's going on with the central pulsar, since this is what's powering the pulsar wind, this is going to directly, whatever's happening with the central pulsar will directly impact the pulsar wind nebula in terms of the particles that it's generating towards its pulsar surface and how that's getting accelerated into the pulsar wind nebula, which is the emission that we are studying. Another problem is how the host supernova remnant is able to expand, particularly how it's expanding into the density of its ambient interstellar medium. So the density plays a pretty big role in that, specifically in how the reverse shock of the supernova remnant is sent back. And so this actually dramatically impacts the pulsar wind nebula when this happens. And so we're really interested in trying to understand the underlying particle populations that are being injected into the pulsar wind nebula, and how they are emitting during the different stages of evolution for pulsar wind nebula. And so I'm going to touch on that a little bit. So just to clarify, we lack clear characterization of the particle injection mechanism. So obviously it's coming from the central pulsar, but how? So what's its distribution? What are their energies? How are they being accelerated through the termination shock? So these are all things that we still poorly understand. And what's kind of directly related to this issue is we don't understand how these particles then cool, which makes the nebula itself have some blast processes going on in the nebula, and we don't really understand that. And so we would like to do that by looking at the broadband spectral energy distribution, which is why we need more gamma ray observations, because the inverse Compton emission is actually really important in understanding these underlying particles. What I'm showing you here is one of many theoretical simulations that have been done in order to try to understand what sorts of information can we gain from looking at their broadband emission and kind of working backwards and trying to understand the properties of the injected particles. So let me start with the top panels. The top panels are the particle spectra. And this is just assuming a simple power law distribution. So at the time of injection, you're seeing these dashed lines. That's the power law distribution that they sent in. And then they allow the pulsar wind nebula to expand. And so these color bars are corresponding to the age of the pulsar wind nebula. So the darker the color, the younger in the evolution it is. And so as we get closer to the red, that's closer to like the present part of that stage. And so in the bottom panels are the associated photon spectrum, broadband spectrum that you would expect to see during these different stages. So in the left panels, I'm showing you the first pulsar wind nebula expansion. So very early on, when the pulsar wind is able to be generated and the supernova remnant is still freely expanding into the interstellar medium, the pulsar wind nebula is also allowed to expand into its surroundings inside the remnant. And so some of the things that are interesting to note is that when you have this power law distribution, you see how quickly it broadens. And you also see that the energy peak is increasing with time, so we're going from purple to red. And this is because the most recently injected part is dominating the spectrum as the pulsar wind nebula is very first expanding, once it's very young. And this is imprinted in the broadband spectrum if you look over here. So this first peak is showing you both radio and X-ray emission coming from synchrotron emission, so this would be our synchrotron peak. And over here we have our inverse Compton emission peak. So this is in the gamma ray domain, which again we have very little observations to kind of back up some of these simulations. And so we see that with time, the synchrotron emission is actually declining. And this makes sense because this is in the expansion phase. So the synchrotron emission should decline because when the pulsar wind nebula is expanding, your magnetic field is decaying. And so we should see synchrotron emission declining with time. Now, conversely, we're seeing the inverse Compton emission increase with time. And very early on in the stages, you will actually see two peaks in the inverse Compton regime. Where this high energy peak right here is coming from the most recently injected particles. So at first, that's what's going to be dominating the spectrum. But as the pulsar wind nebula expands, it starts to become dominated by the older injected particles at all energies. And so if we look at the reverse shock phase, so this simulation starts right when the reverse shock is starting to compress the Pulsar Wind Nebula, and we see some very dramatic changes. And this is a really interesting stage for looking at Pulsar Wind Nebula. And so I can't really reach up there, but you can see that the spectrum is actually narrowing quite a little bit with time. And then it introduces this energy break and then steep drop-off. And this steep drop-off is actually caused by rapid synchrotron losses. So when you have the reverse shock coming back to the Pulsar Wind Nebula, it's crushing it and it's driving that magnetic field back up. So now it's synchrotron emission should be increasing, and that's how you're going to be having some loss processes maximizing in the nebula. And so that part can be reflected in, again, watching how the synchrotron peak actually is increasing quite dramatically. And then the energy break, where you see this is actually decreasing with time. And so this can be seen in how the inverse Compton emission peak is decreasing with time as well. And so there's actually a ratio here. There's a little bit of a relationship. So as synchrotron emission increases, inverse Compton emission tends to decrease and vice versa. And so this could be a pretty unique indicator for us to be able to, with certain supernova remnant systems, this could be a really good indicator to see where the whole system is in terms of its evolution if we can get enough observations and comparisons. And so this is another SED, which is very similar. So the blue dash is showing you 5,000, red is 2,000, and then black is red 1,000. So it's really just 1,000. So it's really just showing you, again, that how if the Pulsar Wind Nebula is allowed to expand, you again see this fluctuation where the synchrotron emission declines while the inverse Compton emission is increasing. And so this is another motivation for us to look in the gamma ray domain, is because as the Pulsar Wind Nebula gets older, the inverse Compton emission tends to dominate. And so we do think that we could actually increase the number of known Pulsar Wind Nebulae in this domain significantly by looking for them in this way. But we need more observations. So the perfect place to look right now is going to be the MEV to GeV. We already have a lot of TeV observations for Pulsar Wind Nebulae. In fact, the majority of TeV galactic sources are Pulsar Wind Nebulae. There are about 20 of them out of, I don't know how many of objects are in the TeV cat off the top of my head. But for comparison, in the Fermi catalogs, the 4FGL, that is the most recent catalog, there are only 11 confirmed Pulsar Wind Nebulae. So we do expect to be able to discover hopefully a lot more Pulsar Wind Nebulae. And we're going to use the data that we get to combine with multi-wavelength data, make this broadband energy spectrum, and then try to kind of work backwards to see what type of information we can get from the underlying particle population, as well as a plethora of questions that we have with Pulsar Wind Nebulae, in terms of how they accelerate cosmic rays, and if they do accelerate cosmic rays, and what mechanisms that would be. So, this honestly has like a multi-purpose to it. So it's really exciting. And so just to end, the point of us how we're going to actually do this is we're going to first start with a systematic search around all known Fermi gamma ray pulsars. There are currently 250 gamma ray pulsars. I'll be a very busy lady. And so we will start there, and then we will also look for gamma ray counterparts of already known Pulsar Wind Nebulae across the wavelengths. And so I will just end there.
Are you thinking also of including imaging information in addition to the spectrum, or just the spectrum?
So imaging with Fermi-LAT?
No.
Just like in general? Yeah, absolutely. Yeah, and doing like multicolor images and seeing how...
yeah, that's one thing. Or if you forecast that there should be a reverse shock, it might show up in the image and you would see it in the radio. So
yeah.
It's just additional information that can support your interpretation.
Yeah, absolutely. I mean, I plan to be like extremely thorough about this because I honestly have a lot of questions in terms of cosmic ray acceleration at the termination shock, and so I would love to look at it at all angles possible. So yes, absolutely.
Questions or comments?
Yes, as a corollary to what you're thing. These photons will also multiply ionize species, so spectrum might also tell you something about these molecules.
Yeah, that's a great point.
Infrared and the optical.
Yeah, awesome point. Yes, absolutely.
Anyway, we wish you great success. It looks like a very important project.
Yeah, thank you so much.
Let's thank Jordan.
So now I have to give you this. Where'd it go? You get that?
Everybody hear me okay? All right, it's great to be here. I gave a little ITC lunch talk about 10 years ago when I was here, so it's great to be back giving another one. So my talk this afternoon is going to be about the exoplanet context for studying giant planets with a large sample size. My talk today is the nearby context of studying two planets in as much detail as we possibly can. And this is a look at Jupiter and Saturn, their interior structure, and how they evolve over time. So as I mentioned, the astronomical perspective allows you to ask questions and answer them that you couldn't ask in the solar system. But more detailed work in the solar system can tell you if you're working from a solid foundation. Just like in stars, we'd like to study the sun in as much detail as possible as we understand stars as a class, or galaxies by looking at the Milky Way. We'd like to look at Jupiter and Saturn, which are our hallmark gas giant planets, and understand them in as much detail as possible as we are trying to understand extrasolar giant planets. So there's a famous paper by Pollock et al. In 1996 that kind of lays out the modern theory of how we think giant planets form. This is time in millions of years versus the mass in Earth masses. And so we think giant planets form when their disks are still around, there's still hydrogen. You form a core of something like 10 or 20 Earth masses of solids. That's the Z mass. That core starts to accrete hydrogen and helium. That's the XY mass. This is called core accretion, core nucleated accretion. And so your final giant planet might be very large in mass with some structure that has some sort of core, and then tens or even hundreds of Earth masses of hydrogen and helium on top of the planet. And so if we take a slice view of what we thought Jupiter and Saturn were probably like, this is as of about 4 years ago, before Juno, before the Cassini grand finale orbits. This kind of plot kind of gives you the lay of the land. The visible surfaces of Jupiter and Saturn are quite cold, something like 135 to 170 Kelvin. But deep inside, it's quite hot, very high pressure. Most of Jupiter's interior is liquid metallic hydrogen, a sea of protons and electrons, a very strongly coupled plasma at tens of thousands of degrees. The visible atmosphere is molecular hydrogen, H2, but there's a transition at around 2 megabars. Jupiter is about 3 times solar. It's enhanced in metals compared to the sun. Saturn, it's a lower mass planet. It's a third Jupiter's mass, lower pressures, lower temperatures in the interior. Less of its mass is this liquid metallic hydrogen. More of the mass is this fluid molecular hydrogen. And so it was noticed by the Galileo entry probe that dove into Jupiter's atmosphere in 1995 that Jupiter's atmosphere, and presumably much of its interior, is depleted in helium compared to the protosolar abundance, which is Y of about 0.275, which we know from helioseismology. And this is important because it probably suggests that there's a helium-depleted region, which suggests that there should be a helium-enriched region down deeper down below. And it actually turns out there was a paper suggesting this might be true by a famous astrophysicist we all know named Ed Salpeter. So Ed Salpeter in 1973 wrote a very short abject letter suggesting that helium and hydrogen might have limited solubility in each other. and that helium might phase separate, like oil and water, from the hydrogen, and that might lead to implications for the interiors of planets generally. And so the idea was picked up by later authors like Dave Stevenson and many others over the years. And it's worth revisiting every decade or so as we get better data about the planets, better first principles calculations about how hydrogen and helium work under high pressure, and better observations. So this is work that Chris Mankiewicz has done in Santa Cruz. Chris graduated. He's now a postdoc at Caltech with Jim Fuller. And one of the things Chris worked on was new evolution models of Jupiter and Saturn. These are cooling tracks, the effective temperature over time. These are sort of Hennier-style evolution models looking at Jupiter and Saturn's cooling. We, of course, know the effective temperature of both planets. And the story that's gone back since the late 1970s is that kind of standard cooling models, there's a wide range of colors here, it doesn't really matter, can reproduce Jupiter's effective temperature at its known age reasonably well. There's been a long-standing shortfall for Saturn. Saturn is much more luminous today than you would expect from a simple, fully convective evolutionary model. So Saturn needs to have some sort of dramatic energy source that gives it much more luminosity today. And that's long been suggested to be due to helium sedimentation. If you have several Earth masses of helium falling down within the planet, that's a change of gravitational potential energy into thermal energy. But what's been lacking is a quantitative assessment of this process for both Jupiter and Saturn. So the idea is that at high pressures, megabar pressures in several thousand degrees, in yellow there might be a region where helium and hydrogen phase separate. There's a limited amount of helium you can mix into hydrogen, just like there's a limited amount of sugar you can put in your coffee. And as a cup of coffee cools off, you can put less and less sugar into that mixture. And so Jupiter probably, we think, maybe just skims this region where helium starts to rain out, where Saturn probably has fallen dramatically into it. So the idea for Jupiter then is that you have a thin range in pressure space where the helium raindrops are forming. This is the excess helium, and it rains down to deeper layers and then just gets redissolved. So slightly depleted, slightly enriched with a thin layer in between. The idea for Saturn, though, is it might be dramatically different if Saturn's interior, this is the lower curve here, has fallen all across this region. And so we've done evolutionary models for Jupiter on the left here. This is temperature over time, the helium mass fraction over time, and the radius over time. And our models can reproduce Jupiter's modest helium depletion and Jupiter's effective temperature. And helium, we think, started raining out in Jupiter less than 1 billion years ago. Jupiter has to have the same physics as Saturn, right? They're both hydrogen and helium. There's the same phase diagram. We can look at Saturn over time. Saturn's cooler. It's cooled off much more quickly, and we think it started to rain helium out about 3 billion years ago. That's dramatically affected its cooling history compared to the simple model, and the helium's been raining out of the atmosphere and falling down to deeper layers. The thing about Saturn, though, is that there's really nowhere for that helium to go. There's not a vast reservoir for the helium to redissolve in. So we think that those helium droplets are actually settling on top of the core. So on the left is a snapshot of a movie of helium depletion in the outer region, helium enrichment down below. In Saturn, we have a movie of what we think is happening going on today. This is the full extent of Saturn's mass shell here. We're losing helium from the outer layers and building up almost a pure helium layer on top of Saturn's core over the past few billion years. I should mention that the hydrogen is liquid metallic, it's ionized. The helium is neutral. So they're not going to have the same conductive properties. So that might well have big implications for how Saturn as a dynamo is generated compared to Jupiter. So the mental picture we're advocating for what Jupiter and Saturn look like in their interiors today are like this. On the left, we have Jupiter with a modest helium depletion, a modest helium enrichment with a gradient region in between, along with a core, which is how big this core is a talk for another day. While in Saturn, we have a prediction of a extreme helium depletion in the outer layers, a gradient region, and then a pool of several Earth masses of almost pure helium sitting on top of the core. And so then in this deep liquid metallic region of both planets would be where this convective dynamo presumably is causing the planets to have their strong magnetic fields. So the conclusion then is that helium phase separation and the subsequent rain of helium to deeper layers can explain Jupiter and Saturn's thermal evolution, as well as Jupiter's known helium depletion, and we can make a prediction for Saturn's helium depletion. The Cassini mission did not have an entry probe into Saturn. The probe, of course, went into Titan, but it would be great to one day have an in situ probe into Saturn's atmosphere. This helium rain leads to a dramatic difference in the interior structures of these planets today. You cannot really think of them as carbon copies of each other, even though they're obeying the same physics that leads to differences in their structure today. We have suggestion of a layer of nearly pure helium on top of Saturn's core. No one has yet done three-dimensional dynamo simulations looking at this configuration and how that might explain the fact that Saturn has a much weaker magnetic field than Jupiter has, but this might be part of the issue. And the measurement of the helium to hydrogen ratio in Saturn's atmosphere from spectroscopy is still ongoing. It's a very subtle observation because helium tends to collide with hydrogen and subtly affects the hydrogen spectrum. That's typically how one tries to measure the helium abundance. But an entry probe would be best, and that's something that past decadal surveys in the solar system have thought about, and it's something that might happen in the future. Thanks. I'm happy to take questions. Those are great questions. So the expectation is anything probably more massive than about 1.5 Jupiter masses won't cool off enough in the age of the universe to fall into this helium depletion region. So it's probably limited to Jupiter-like planets and less massive. Could you test it with seismology? That was your question, right? That's a great question. It's actually what Chris is doing with Jim Fuller right now. So Jim and Chris have both looked at Saturn seismology in the past. And there has been good evidence that Saturn may have a deep composition gradient on top of the core that might allow G-modes to propagate. And it's possible that that helium layer could be part of the story. It's not obvious right now, but that's one of the things that they're looking at.
I was just wondering if there's enough spherical asymmetry in the layers that you might, through gravitational effects on some of the bodies around it, see any effects.
That's a great question, too. So what we can say is that the model we outline is consistent with the gravity field, but that there are models that don't have this much helium depletion that are also consistent with the gravity field. So it tends to be non-unique in its solutions.
You mentioned that this process also can operate on lower mass planets.
Mm-hmm.
I'm wondering, like, is it possible that it's acting in Uranus and Neptune, and Uranus is retrograde, and like that kind of be?
Yeah, it's a great question. It's possible this could happen in Uranus and Neptune. It's also possible it might not. And the reason why is that at 1 megabar, that's where you're transitioning from this molecular hydrogen H2 to the liquid metallic hydrogen H+, and it's a continuous transition. We think in Uranus and Neptune, the pressure at the bottom of the hydrogen-helium envelope is not this high. It doesn't reach a megabar. There are certainly pressures that high within Uranus and Neptune, but we think by then you've transitioned to the fluid, ionic, watery layers. And so then this would not happen. But if we do have an entry probe into Uranus or Neptune and we did see helium depletion, that would radically alter our models because it would suggest that there was a deep reservoir of hydrogen that would be having this happen.
Some of the lower line molecular hydrogen lines are in the mid-infrared. Because it doesn't have a dipole moment, it should be fairly optically thin. Could you conceivably measure the pressure broadening of these H2 bonds? At these temperatures, they should be fairly bright to establish just how deep the molecular hydrogen layer goes.
So yeah, we can see molecular hydrogen as far down as we can go. That's typically down to tens of bars, but here we're looking at much higher pressures than that.
That just becomes optically.
It just becomes optically thick. Yeah. The way people have tried to measure the helium abundance is kind of interesting, though, because H2 molecules collide with each other, and we can to make collision-induced absorption. And the heliums also colliding with the hydrogens kind of shift those features a bit. So people have tried to fit mid-infrared spectra by adjusting the helium to hydrogen ratio to best match that observation. That's the best people have done so far. It's kind of a subtle effect, though.
By the way, John, the fact that Saturn spins implies that if you have a helium layer on top of the rocky core, it might actually flatten more than the rocky core is. So the rocky core might be spherical.
Right.
And then on top of that, there will be a fluid which is flattened.
Yeah, that's true. They would have different responses. Yeah, I think that's true.
Interesting calculation to check if from gravity observations you can consider.
Yeah.
Any other comments? Let's thank John.
All right. Thanks a lot. Thanks for the reminder. I totally forgot.
No problem. You're welcome, Shai. There you go.
Okay. So what I'd like to tell you about today is a new simulation project that I'm working on together with Paco Velasquez Navarro, who's leading the project, and Daniel Angel-Sangalzar, my colleague at CCA. So we call this project CAMELS, it's Cosmology and Astrophysics with Machine Learning Simulations. So the motivation is that we'd like to extract the maximum available cosmological information from galaxy surveys. And this includes, so the cosmological parameters we'd like to exclude, those of the standard cosmological model, as well as possible extensions of that. And galaxy and surveys applies for galaxy surveys, clustering, weak lensing, SZ, X-rays, large upcoming surveys of many kinds, which contain information both about the cosmological model as well as about astrophysics. The challenge is that, or two challenges that I'd like to point out, is that the information is really everywhere, while typically we're using some kinds of summary statistics like power spectrum very typically, or void statistics, many ways that we're trying to summarize this information, but actually we don't know for sure what are the best summary statistics, and we'd like to extract as much information as we can. Another big challenge is that a lot of information is being masked by astrophysical or baryonic processes that are very complicated, that we're still trying to understand on the galaxy formation side, but are masking information on the cosmological side. So what we would like to do is extracting as much information as we can while marginalizing over our lack of knowledge about the astrophysics. And also, the other side of the coin is that we also like to understand the effects of astrophysics on these observables, large-scale observables. So the tools we use in this project to try to address both of these aspirations are cosmo-astrophysical simulations, namely cosmological simulations that include gas and baryonic physics, as well as then neural nets, which we can see as essentially universal approximation machines. Approximation of what? Of the relation between the astrophysical parameters and the observables. So I'd like to just briefly mention a couple of recent successes of applying machine learning to cosmology. So there are papers that are using n-body cosmological simulations to try to extract cosmological parameters, predict cosmological parameters, and compare to the ground truth of the simulation just by, for example, feeding it with a large-scale structure distribution of matter. This can be done with some success, and perhaps even better than just traditional power spectrum analysis. Another example, less directly related to CAMELS, but still I think nice to point out, that one can use neural nets to actually learn the H1 neutral gas density field from a simulation like Illustris G, shown here, and then generate random fake such fields, shown here in the bottom. And it's been shown that they can reproduce statistical properties of those fields very well. So neural nets are able, generally, to learn the cosmological structure formation, I would say. Now, again, before going into the CAMELS simulation, I'd like to show a toy model that will kind of convey the message of what we'd like to do with the complicated simulations. So we'd like to extract the cosmological information from, let's say, a noisy power spectrum. So we'll start in a case where there are no baryonic effects. So we set up some power spectrum here, just a power law for simplicity, and there's some noise that represents cosmic variance. And we try with a neural network, a very simple neural network, to predict, to extract the information about the parameters that define this power spectrum. This is simply its normalization and its slope. On this plot shows the error on the extraction of this parameter, for example, the amplitude of the power spectrum, as a function of K max, of the maximum wavelength that is used to perform this extraction. So we start by using just the largest scales, and we get a large error. As we include smaller and smaller scales, there's more information, and the error drops down. So that's very simple, and essentially the neural net can do as well as maximum likelihood analysis. Now what happens when we add baryonic effects? So we do this in this toy model in a simple way. At a given scale, so we have just an example for another power spectrum. At a given scale, we break the power spectrum and make it completely random with its own slope and own amplitude. Clearly, then, this part does not, representing the change that baryonic effects cause, contains no information about the cosmological parameters, or is essentially represented by the power spectrum in this part. And indeed, the neural net learns to marginalize over this part. So it contains, the error just doesn't rise, but stays constant. Simply, and it's not being told what is this scale. It just learns that there is no information in this part about this part. Now, another toy model for the effects of astrophysical parameters, we still set the slope in this part randomly, but now we make the power spectrum continuous. So now as you go to higher and higher K, even though the slope here is completely unrelated to here, the level of the power spectrum here contains some information about this particular point where they connect. So there's a little bit of residual information in this part about this part. And indeed, the neural net is able to extract the maximum information, and the error continues going down as you integrate towards larger K. So this is essentially what we want to do now with full cosmological simulation. So what is the CAMELS suite? So we have right now 2,000 cosmological hydrodynamical simulations in boxes of 25 megaparsec over age. 1,000 of them have been run with essentially the Illustris G model with the AREPO code, and 1,000 of them with the SIMBA model, which is another code used for another large cosmological simulation, the SIMBA simulation, used with a different code and different physics. But it's not exactly 1,000 with this model and 1,000 with this model, but rather variations around these models. And the variations vary both cosmological parameters as well as 4 astrophysical parameters relating to stellar and to black hole feedback. We sample this 6-dimensional space with the Latin hypercube, so that these 1,000 simulations actually have high resolution in each individual parameter. We also have 2,000 corresponding dark matter only simulations, and I should point out that these boxes are different, are made with different phases, different initial conditions. We have an additional smaller suite where we use one box, so given set of phases, same initial conditions, but varying one of these 6 parameters at a time, as opposed to machines. For humans, it's easier to understand this kind of suite. Okay, and what do we do with it? So first exercise, we feed it the power spectrum, matter power spectrum that we get from each of these 1,000 simulations, or a bit smaller set than that we use for the training set. We feed it to a random forest and train it to extract the omega matter and the sigma 8, essentially marginalizing over the astrophysical parameters. And then when we use the test set, this is an example for the variation in the in the matter power spectrum that we get with this large suite of simulations. Then we use this trained random forest on a test set, and we get this prediction of omega matter and sigma 8. So there is scatter, but what we show is that we can achieve a similar thing that was done previously on n-body simulations, but with simulations that vary the astrophysical parameters and vary the power spectrum. Oh, I should say, this is the ratio of the power spectrum in the astro simulation over the corresponding dark matter simulation. Now, let's move to a more stringent test. We use the same training set, but then we try to predict for the test set. Oh, and I should say, these are still early days. We will improve significantly on that. This is still a very simple machine learning model. And also, we're only feeding it the power spectrum. There's a lot more information, as I suggested earlier. Now, the strangest test is to use the elasticity NG suite and try to predict the parameters from a network that learned this from the Simba suite. Indeed, we get more scatter because the astrophysics works differently in these models, but still, given that it's early days, we see this as a very promising early result. Okay, so that was for marginalizing over cosmology, over astrophysical parameters, but there's also interesting astrophysics that we can do with this large simulation set that we have. So here I'm showing different quantities like matter power spectrum or baryonic fraction of halos, star formation history, and these shaded regions show the full range, or not the full range, but the typical range covered by these two different suites. So we see there's a lot of overlap. Some of it comes from the fact that both of these suites vary in the astrophysical, in the cosmological parameters in a similar way. But there's also significant differences that we can try to learn astrophysics from. And in particular, it's interesting that the responses to changing these individual parameters, for example, the mass loading factors of galactic winds, can be qualitatively different between these two sets. So, for example, changing the mass loading factor of galactic winds, you can see that in the elasticity NG simulation, when we use a lower mass loading, the matter power spectrum goes up, while in the Simba model, it goes down. So I think there's a lot of things to study there. And lastly, as I mentioned, we also are trying to predict observables from the astrophysical parameters. So we train another neural net to go from the values of these different 6 parameters to the star formation history in the universe, and we get to a few % accuracy. So this is very promising for future calibration of large models. You could essentially provide it with, combine it with an MCMC and get the parameters that would give you the star formation history that you want. And I'll stop here. Thank you. I recommend that we hire more machine learning people.
I have a question, and I know you said these are early results. Mm-hmm. So, with that being said, mm-hmm. I think the results with the random forest regressor are really promising, and I'm interested to know if you've looked at what power spectrum bins are the most important to the random forest regressor, because you might be able to get some sense of what it is that the machine learning is picking up on, or what scales it's picking up on.
Yeah, so it's definitely it's more information in the larger scales, because we see that the astrophysical parameters change the smaller scales. The scatter is much larger on the smaller scales, but I don't have a quantitative answer for you. Yeah.
So certainly I see a correlation there. There's also a fair bit of scatter, and the scatter looks comparable to or larger than current limits on those parameters. So is that worrying?
Not yet. I think so. This is really early. This is just a kind of a proof of concept. Yeah.
Can you describe in a simple way, this is probably a very naive question, the differences between Simba and Illustrious that we can see? What causes the difference in the results?
Yeah, so we haven't really dived into that at all yet, but I think this is something that quite unique that we can do with this set. So we're looking for students.
Okay, last question.
If you go to the next, no, not the next slide, when you applied the Simba learned on Illustrious, where is that floor of prediction coming from?
Yes?
Yeah.
We don't know. Yeah, good question. Yeah.
Sorry, another question.
Yeah.
So I was wondering how much this scatter depends on your training section, because it's like, if you just change the way that you train, actually your machines, whatever, is there any possibility to shrink it or combine different methods?
Yeah, I think so. I hope so. So it's, as I said, early days. It's an initial model. So well, definitely this is one of the first things we want to do, improve the regressor.
We need to move on. Let's thank you.
Is it already on?
I think so. Yeah, they'll turn it on when you start talking.
Great.
Is that okay there?
Yeah, should be fine. Thank you. Okay, hello? All right, all set. Great. So I'm Nathan Sanders. It's just a privilege to be back at the CFA to see so many friends. So I want to thank Paul, Avi, everyone else for inviting me back. So as Avi mentioned, I came to the CFA for my PhD. I worked with Alicia Soderberg here, fantastic mentor working on core collapse supernova observations. And since then, I've been working as a data scientist in the entertainment industry. So I went to Legendary Pictures, got to start one of the first data science groups in Hollywood there. I worked with one of our colleagues, Jonathan Foster there, who I know many of you know well, for a long time now. We were acquired relatively recently by Warner Media, which is where I am now. But I have the pleasure not to be able to speak to you today about the work that I do personally, but about the work of hundreds of other people that I'm not going to take credit for, but going to try and promote to you a little bit. So the first question I wanted to ask is, how many people here have read an Astrobyte? Show of hands. Oh, very good. Okay. I wasn't sure what response I'd get to that, but almost everybody. That's fantastic. So maybe I don't need this slide, but in case you're not familiar with Astrobytes, here's the problem that we're trying to solve. I want you to think back to when you were an undergraduate student. Not as far back for some of you than others, but think back to when you were an undergraduate student, when you were trying to get involved in research for the first time. If your experience was like mine, you might have gone to a professor and said, hey, I want to get involved in your research. How can I help? And if your experience was like mine, they probably handed you a giant stack of papers. They said, go read this. Some of you may have done this recently. When you're done reading that, come back to me and then you can help. And of course, that's a very difficult thing for a young student to do. First of all, of course, there's jargon. There's words that students at that age simply don't know. But also, there's decades of embedded context from the field, citations, methodologies, experiments that unless you've been in the field for years, you just can't possibly know. So the goal of Astrobytes is to translate impenetrable papers like this one into short and accessible summaries that undergraduate students really can learn from and get involved in research. So we actually have two missions at Astrobytes. So one is to provide that educational resource for undergraduate students, but not everybody knows this. We have a secret second mission, which is to provide professional development experience to graduate students, to help graduate students get involved in science communication, science writing, and also the editorial process and student leadership generally. So Astrobytes was founded here at the CFA in 2010 by myself and 5 fantastic colleagues who I know many of you know well. And then since then, we've been joined by many, many more graduate students. This is just a chart showing the growth of our authorship over time. You can see in the beginning, we sort of were haphazardly growing a group, and over the last 8 years, we've had a very systematic process because we've been oversubscribed for bringing in new authors. So in total today, we have more than 150 graduate students truly around the world who have collaborated with us on writing these Astrobytes. This is just a map of our current authors right now in 2020, even more diversity than this if you look back across our whole author group. So Astrobytes has now been operating for 10 years. This is an exciting anniversary for us. 150 graduate students, 2,500 Astrobytes we've published, more than 4 million reads, page views of our Astrobytes. And one of the things that we're most proud of is that while we continue to be a student-led, editorially independent group, we are also partners with the AAS. We have the privilege to join them for AAS meetings and be sort of an official partner covering the science that's presented there with them. So maybe the thing I think is most exciting about Astrobytes is that it's proven to be a very scalable, reproducible model. So now, in addition to our English language original Astrobytes site, we have astronomy publications in 3 other languages, Spanish, Portuguese, Farsi, and then we have about a dozen other Bytes sites that have spawned in other scientific fields. So in the physical sciences, we have Particle Bytes for particle physics, we have PER Bytes for physics education research, we have EnviroBytes for environmental science, ChemBytes for chemistry, and many, many more. So I do hope if you have interest in those other fields, you'll check out their sites as well. I did want to highlight some of the ways that you all who are teaching, if you're a TF or if you're a professor, can use Astrobytes in your own classroom. We have 4 different models for doing this, and we've published ready-to-use lesson plans together with my colleague Ashley, who's here at the CFA, and several others. We've put together lesson plans that are ready for you to use in your classroom, integrating Astrobytes and helping students to do this kind of synthesis in science writing. So we encourage you to check that out. So it turns out Astrobytes is not the only graduate student-led, internationally grown science communication initiative that was started here at the CFA. So from Astrobytes in 2012 emerged another program called ComSciCon, the Communicating Science Conference Series. So I'll tell you all about that, but to motivate it, I wanted to say a few things. So first of all, why is science communication important to us as scientists? So I hope you all can answer this yourselves, but I'll give you my feeling about this, which is that I think that the only value the work that we produce as scientists has is the value that we actually successfully communicate to other people. We can do the most impressive, accurate, rigorous, groundbreaking work imaginable, but if we can't actually convince someone else that they should care about it, that that's important to them, that it should change their own thinking, then it simply has no value in the field. So this is why science communication is a critical skill to all of us individually. And then the next sort of motivation for us is who should be doing science communication? Who should be equipped to do this work? And to answer that, I would point to some numbers. So a lot of you may know this number that comes from the NSF Science and Engineering Indicator Survey of all the universities in the United States. They estimate across STEM fields there's about 90,000 faculty members. So does anyone know roughly the number of postdocs? Is it more, is it less? It probably depends on how you count. So granted, according to the NSF and their criteria, there's about half that many postdocs in the US. Does anyone know the number of graduate students? Is it more or less? It's a lot more. So this may not be surprising, but for every faculty member, there's about 8 graduate students, master's and PhD. For every postdoc, there's about 17 graduate students. So when we think about who does the work of science, who is doing research, I think the answer is it's graduate students. And if we want to engage with the public, if we want to do civic science, I think it's incumbent on us to empower graduate students to do that type of communication work. So that's what we're trying to do with Astrobytes and with ComSciCon. So ComSciCon is the Communicating Science conference series. It's organized by graduate students, including Harshal and others in this room, and it's operated for graduate students. So we've been operating since 2012. We have 2 big programs. We have an annual flagship workshop. I'll say more about that in a minute. And we also have a network of chapters, ComSciCon events, organized by individual communities around North America and Europe. So ComSciCon also founded not only by folks at the CFA, but by a lot of folks at the CFA. Again, a lot of colleagues that we know well. So I tried to find recent photographs of everybody, but for those who know Sukrit, this is a very old photograph of him, but when you have a photo of yourself presenting your science to Barack Obama, it's the only photograph that can ever be used to talk about you in the future. So it's just been a pleasure for me and for the rest of us to be a part of the ComSciCon community because it's truly interdisciplinary. It's has a large presence in astronomy, but also students from all sorts of other fields. And it's, I think, a rare opportunity for scientists at the graduate student level to interact and share ideas across disciplines and to really practice the communication that makes that possible. So for any graduate student in the room, or if you work with graduate students, our 2020 ComSciCon flagship event is back in Boston this year. It'll be downtown in June. Applications are actually closed now, but we have a late application up, so if you are very interested, please go and put in a late application. ComSciCon events are always free to attend. We don't charge graduate students any fees, and we also, if you're outside of the Boston area, we provide travel support so that you can come regardless of your ability to pay to ComSciCon. We do have chapters all around North America, and new this year in 2020, we have our first ComSciCon event in Europe, ComSciCon France. So we're very excited to be expanding in that way. And of course, one of the most important things I have to do, I mentioned ComSciCon is a free event. That's possible because of amazing support that we've gotten from institutions and individuals, including many folks represented at the CFA. So I do want to thank the department. I want to thank the Faculty of Arts and Science, GSAS, the Provost's Office, the AAS, and several individuals. Pegah Hurley has truly helped us create the infrastructure that makes it possible to run ComSciCon, and she's amazing. Avi, Alyssa has been our faculty sponsor since the very beginning of ComSciCon, and John has joined us for several events as well. And I just wanted to leave you with one last thought. So, of course, Freeman Dyson passed away last week, and one of the things that's been most fun for me at Astrobytes is interacting with and meeting really amazing astronomers through the work that we cover on the site. And we had the opportunity to cover a few different things that Freeman did over the years. This is a paper I think is just amazing. If you don't remember this, in 2012, Freeman Dyson worked with Bill Press and did really transformational research in game theory. They published a new analytical solution to the prisoner's dilemma, which I think really changed a lot of how that classical problem in behavioral economics and game theory is considered. So I think this is just an amazing story of interdisciplinary collaboration. We've got a physicist working with an astronomer turned biomedical data scientist, and together they're working on a game theory problem. Really inspirational. And then lastly, I just wanted to share, this is something that Avi actually made a connection to help us publish. After Avi did some work on the far future of cosmology, which I'm sure many of you are familiar with, he had this remarkable email exchange with Freeman that led to this remarkable quote that I've got highlighted in red here. So if you want to know the full backstory behind Freeman taking this unusual position, I encourage you to check out the Astrobyte. The whole conversation really demonstrates the wit and the creativity of both Freeman and Avi. So I'll leave you with that thought, and thank you again for joining.
Indeed, the universe is much less imaginative after Freeman passed away.
I was wondering if there's any overall organization that acts something like quality control for astrobytes in the different areas like chemistry and so forth and so on.
Excellent question. What is the quality control for our byte sites? We have professionally trained world expert editors at Astrobytes, which are all the graduate students in our collaboration. So we have a peer editorial model. Each Astrobyte is reviewed, and often we'll go through 2 rounds of review by other graduate students before it goes up on the site.
I think this is fantastic and have from the beginning. And I think you're doing absolutely the right thing by focusing on graduate students, because that's where the numbers are now, and they, in the future, will be the people who are communicating science. But I have one question, and that is that a lot of people are not now graduate students, and they don't really have the best methods to communicate science to the general public, but they're often asked to do it. And, it's just something that one is never, until you guys came along, never trained to do. So do you have any plans to sort of look at how you might engage some of the older folks or people who are doing other things into what you do, or advice maybe for how they might get something started?
Such a great question. I certainly agree that scientists beyond the graduate student level need to be excellent communicators. We as a field need them to be excellent communicators. We've chosen to maintain a powerful and strict focus on the graduate student population. We serve about 1,000 students a year right now with ComSciCon, and that's, as you saw, a small fraction of the total population. We have a lot of work yet to do there. But we also hope that the work that we do with graduate students will propagate. So the students that because we're very oversubscribed, the students that we try and select for our ComSciCon are the ones who have the capacity to be leaders, to go back to their own institutions and create science communication programs that involve yet more people. And we know from seeing amazing things that students have done over the years that that does then include people in other parts of the population. And of course, those students, as you pointed out, go on into different, more senior leadership positions themselves and then bring those skills with them. So we're doing our best just to meet the graduate student needs right now, but I certainly agree that there's a larger task out there.
The fact that 8 out of 9 students continue to some other type of job, I guess, highlights the importance of the role we do as educators also, because they propel the society in so many different ways than we do. And so the connection to the outside world, again, is very much important, and that's what you are promoting.
Well, yeah, thank you for saying that. I think that's absolutely right, and I benefited so much from my advisor, from Alicia, really emphasizing the importance of communication within our field. And I've done my best to take that into a new field now. I hope that everyone here who mentors students will think similarly.
Well, we are grateful for what you're doing. Keep doing what you're doing.
Well, thank you for having me back.